Hello, welcome to a video on section 7.2, the area between two curves. And also hope that many of you are enjoying the start of your 3-day weekend. Hopefully you have some fun stuff planned like March Madness or Sadie's last night or going to the beach later this weekend. Anyway, so let's talk about the area between two curves. So 7.2 kind of takes what we've done with definite integrals and takes a step further. So again, we're trying to look at how we can apply the stuff that we've learned from chapter 5 and 6. And so here we're going to talk about, again, the area between two curves. So let's say that we know that f of x is greater than or equal to 0. So like right here, we have the graph of f of x in the interval from a to b. So for sure, according to what we see right there in that interval, f of x, all the y values in that curve are greater than or equal to 0. If that happens, then the area between f of x and the x-axis, and we've kind of already talked about this before, we know this is true. It's a definite integral of f of x times dx from a to b, right? So that's going to be the area between the curve and the x-axis, in between a and b. We know this, right? But what if we try to find the area between f of x and another function, say g of x, like in the case right here? Then what you could do, if you think about geometrically, is that you take the area between f of x and the x-axis, which is this right here, and you take the area between g of x and the x-axis, which is right here. And again, they're following the same interval from a to b. If you subtract the area for f of x with the area for g of x, you wind up getting the area between the two curves, right? So naturally, we could just say that using our properties of integrals, that the difference of f of x and g of x, or more specifically f of x minus g of x times dx, if we integrate that from a to b, that'll get us the area between two curves. But we are assuming, very, very important, very, very, very important, I cannot stress this anymore, that f of x is always bigger than g of x on a to b. Or basically, the y values on your upper curve always greater than y values on your lower curve. For the same x values. So for example, if this were like x equals 2, the y value on f of x is of course greater than the y value on g of x. Or say that this was 4, the y value at x equals 4 for f of x is greater than the y value at x equals 4 for g of x, right? So very important that in order to do this with confidence, to find the area between two curves, your upper curve is f of x, your lower curve is g of x, and you got to make sure that the y values in the upper curve are always greater than the y values in the lower curve. So if that's true, the area between two curves, f of x is greater than g of x in your interval from a to b, then you wind up having this. Now there is a time where the y values could be the same, so because it is greater than or equal to, so I should have said always greater than or equal to the y values on the lower curve. So let's look at an example where we can try this. Let's say we're considering y equals secant squared x, y equals sine x from 0 to pi over 4. So here we got 0, here we got pi over 4. Now remember, secant squared x is like 1 over cosine x, then squared. So if you want to graph in the calculator, that's how you type it in. It would look something kind of like this. And sine x, hopefully you realize, is just kind of like that. and we're looking for the area between the two curves. So again, I started by graphing the curves and doing some shading. Of course, the one that's higher is the secant squared x, or y equals secant squared x. So if I want to find the area between the two curves, I'm just going to integrate from 0 to pi over 4, make sure that secant squared x is the upper curve minus sine x, which is the lower curve, times dx. So secant squared x is upper, sine x is lower. And we see that visually. If you take the antiderivative of each of those trig functions separately, you wind up getting this. And of course, we're trying to integrate from 0 to pi over 4. So if we plug those values in, you get 1 plus root 2 over 2 minus 0 plus 1. So you just get root 2 over 2. So that's the area between secant squared x and sine x is root 2 over 2. Great. And another thing to keep in mind is that you always want to sketch the graph, label with equations, which actually I didn't quite do. So that was secant squared x. Of course, that's y equals sine x right below. And of course, shaded area, which I did do. So this way you can visualize the problem. So very, very important. You want to visualize the problem, because it helps you to solve it, right? Now you could do this in the calculator. So I pull out the Wabbit app. Excuse me. So you can always just graph it like 1 over parentheses cos x squared sine x mode. We're in radian mode. And I like to graph in the trig mode, so we'll go z trig. So there's secant. And of course, you see sine. And actually, I probably should adjust my window. Let's go to 0 to 0.25 pi. The interval, I don't know. Doesn't really matter. Graph it. And so that's what we're basically graphing. Or, I don't like that y window. Let's say I went from -2 to 2. And actually, let's make that pi over 2. But remember, we want this at pi over 4, which is probably right over here. So we want this area right there. Okay. And then, of course, if you want to solve this in the calculator, you can just do alpha window from 0 to 0.25 pi, alpha trace y1 minus alpha trace y2 with respect to x, which is root 2 over 2 if you verify. A little hard to do with this clicking. Yeah, so, we verified the answer, which you can always use your calculator for. Now, question here. So now we're at the beginning of page 2 of notes. Would this result always hold true if one or both our functions lie below the x-axis? Well, let's see. Let's say you were told that the integral from a to b of fx times dx is 5. Okay, so you know this. And for a to b for g of x is -3, which makes sense because that's below the x-axis, right? Well, using my properties of integrals, I could separate, fx minus g of x to their own integrals. If I do 5 minus -3, I get 8. And the area between the curves should be 8, right? Because again, that's just 5 right here and 3 right there. Let's look at another one. Let's say both of them are below the x-axis because the previous one, only g of x is below the x-axis. So f of x, see the integral for that one is -7. The integral for another one is -17. So we expect the area between these two curves to probably be 10 if you subtract the two correctly, and that's what happens. These are properties of integrals. You want to get the same thing. Because I guess this portion right here was -7. All that was -17. The difference is 10. So the conclusion is that this relationship that we're talking about, find the area between two curves, will always, you could do the integral of fx minus g of x dx from a to b, will always work provided that f of x is always bigger than or equal to g of x. That's why we always have to look at upper and lower. You always want to be able to do that correctly. Let's try one more and summarize all this. So say you got y minus 2x squared, which I know is going to look kind of like this. And y equals -x. It kind of looks like that. And I want to find the area between the two curves, which is this. So notice how I graphed this so I can visualize it. Very important. You want to visualize the problem. And also helps to find points of intersection. Because the boundaries weren't explicitly told to us like they were in some of the other problems. So to find points of intersection, hopefully you guys remember to just set the equations equal to each other. You wind up getting quadratic, which you can easily factor. And maybe it might help to be in pause the video so you can factor it and replay it. Oops. I need to go back to algebra 1. Forget to factor that wrong. There we go. X equals -1 or 2. So when x equals -1, y is going to equal 1 if you plug it back into the equation. And of course, if x equals 2, y is going to equal -2 for each equation, which explains our points of intersection between the two curves at those two places. So what that implies is that if I'm trying to find the area between the two curves, I'm going to have to integrate from -1 to 2 of 2 minus x squared minus x squared, because, sorry, minus x. Minus -x. Remember, this is the upper, the parabola. The line is lower. The line was -x, the parabola was 2 minus x squared, so it's 2 minus x squared minus -x. So to clean that up, it's -x squared, excuse me, plus x plus 2. Take the antiderivative of each of those terms, you should get this. And you're plugging in 2 and then -1. So if you just trust me here, you should get 4.5. I mean, the arithmetic I think you guys should be okay with. I don't have to go through that whole process. But the answer should be 4.5, and the answer should be positive, right? Expect positive answer. Otherwise, you did it wrong. The answer's got to be positive, so be careful. If you got -4.5, that would mean that you switched the lower and upper curves, so be mindful of that. So in summary, sketch the graph. Very important. and of course label with equations and shade your area. Again, I have a bad habit of not labeling. That's y equals 2 minus x squared, which is upper, y equals negative x, which is lower. Number 2, find points of intersection. And number 3 is f(x) greater than or equal to g of x everywhere. Now, if that's not true, there's going to be another way we're going to do this, which we'll talk about later. But for now, we're not going to do that. Does f(x), and if so, we can move on to step 4, which is that the area will be the definite integral from a to b for f of x minus g of x times dx. Again, granted that we're doing upper minus lower. And remember, the upper function will be y in terms of x, and the lower will also be y in terms of x. And you always want to guarantee that the y values in the upper function are greater than the y values of the lower function for a particular x value. Okay, that's the end of the video. Enjoy the rest of the weekend. Hope you got a lot of fun stuff planned, and I will see you guys later.